ASK Aviation School.
A thunderstorm is a highly localized, violently unstable thermodynamic engine. It is a system built entirely to convert latent heat into lethal kinetic and electrical energy. The conditions that trigger these engines exist on a massive scale. During the Indian pre-monsoon season, between April and May, intense daytime heating of the landmass creates widespread, deep atmospheric instability. Despite their vast regional origins, the true threat to an aircraft lies entirely in the microscale physics hidden within individual storm cells. From the outside, a cumulonimbus cloud presents a seemingly soft, visible boundary. Inside, its structure is capable of producing golf ball-sized hail, localized microbursts, and conditions that induce complete instrumentation failure. Navigating a cumulonimbus requires aligning flight parameters with the specific life cycle of the cell, as the mechanical and aerodynamic hazards change depending on the storm's stage of development. Inside the cell, the kinetic environment subjects the airframe to localized forces that can rapidly exceed standard structural and operational limits. This chart visualizes the baseline condition required for a thunderstorm to form. It plots a steep environmental lapse rate that exceeds the saturated adiabatic lapse rate through a deep layer of the atmosphere, creating a distinct zone of instability. This unstable moisture requires a physical trigger. Severe daytime solar heating can start the ascent process, or it can be initiated by orographic lifting, where terrain forces warm surface air abruptly upward. This initiates the cumulus stage. The forced ascent causes clouds to tower rapidly, reaching heights of 8 kilometers. During this phase, strong updrafts completely dominate the cell. Air is drawn in from the base and sides, achieving vertical speeds up to 100 feet per second. As the instability cloud grows, it pulls in surrounding, unsaturated air. This process, known as entrainment, evaporates some of the cloud droplets and tests the storm's momentum. If the surrounding humidity is high enough, entrainment fails to arrest the cloud's growth. Evaporation is suppressed, and the thermodynamic engine accelerates. This rapid vertical scaling is the silent preparatory phase. The cloud is hoarding immense kinetic energy that it is about to unleash. The mature stage begins the exact moment heavy precipitation initiates a downdraft within the cloud. As precipitation falls, evaporation keeps descending air saturated. It remains colder and denser than surrounding air, accelerating downward at up to 40 feet per second. For an aircraft, the most critical zone inside this system is the altitude band where temperatures range from 0 to -10 degrees Celsius. Here, the massive upcurrent suspends soft hail. These small stones are violently carried up and down the freezing band, continuously striking supercooled water drops that freeze around them to create layered, rock-solid clear ice. These stones can rapidly build to the size of golf balls. At flight speeds, large hail can obliterate radomes, destroy leading-edge surfaces, and shatter transparencies. Those same supercooled water drops present an immediate airframe icing threat. Clear ice builds up rapidly on the aircraft skin, altering the lift-to-drag ratio, while ingestion into the engines threatens immediate turbine flameouts. This precise freezing band is also where the cell generates the highest frequency of lightning strikes. The sudden brilliance is intense enough to require pilots to turn up cockpit lighting fully just to preserve their night vision. The mature stage is where the cumulonimbus cell converts its moisture into a multi-layered gauntlet of structural and aerodynamic threats. When that dense, cold downdraft strikes the surface, it spreads laterally with significant force. This generates a microburst, a highly localized wind shear event. An aircraft flying through this outflow can instantly lose a 40-knot headwind and be struck by a 10-knot tailwind. Microbursts are uniquely lethal during the approach phase. The sudden loss of lift forces an aircraft below its intended glide slope when there is minimal altitude left for recovery. Eventually, the severe downdrafts choke off the updrafts, and the cell enters the dissipating stage. Reduced vertical momentum causes the top of the cloud to spread laterally, forming a massive ice crystal anvil. The cold outflow from this dying cell then acts as a wedge, driving under adjacent warm air to trigger a chain reaction of new thunderstorms. A dissipating cell remains a threat. While its internal engine shuts down, its surface outflow is actively laying the groundwork for a regional squall line up to 15 miles ahead. Total avoidance is the only guaranteed defense. Pilots utilize onboard weather radar and ATC rear-up codes to maintain a wide physical separation from active cells. But if an aircraft is boxed in and penetration is mandatory, standard flight configurations are no longer safe inside the cell's extreme kinetic environment. This diagram outlines the required altitude protocol. The aircraft must cross strictly below the freezing level or climb well above 25,000 feet to bypass the chaotic middle zone where hail and turbulence are most severe. Inside the cell, pilots face a precise speed paradox. Flying too slow through severe downdrafts risks an unrecoverable aerodynamic stall. Conversely, flying too fast through vertical gusts can subject the airframe to stresses that exceed its design limits, leading to structural failure. The only way to survive the physical forces of the cloud is to fly a mathematically rigid middle ground, exactly 1.6 times the stalling speed, with flaps and undercarriage fully retracted. Inside the cell, sensory deprivation takes over. Forward visibility drops to 20 meters, and the airframe is battered by heavy, freezing rain and ice particles. Under this barrage, the aircraft's pitot-static system can become partially or completely blocked by water and ice accumulation. This triggers an immediate instrument cascade failure. The altimeter, vertical speed indicator, and airspeed indicator begin to fluctuate wildly, corrupted by localized pressure variations and ice blockages. This creates a scenario where survival depends on a counterintuitive action. The pilot must suppress their primary flight training and disregard fluctuations in altitude and airspeed. Attempting to chase the altitude or execute turns to correct the flight path will only amplify the strain on control surfaces and risk putting the aircraft into a fatal attitude. Surviving a cumulonimbus is an act of supreme discipline. It requires ignoring broken instruments solely on a constant attitude to simply ride the storm until the aircraft emerges on the other side.
ASK Aviation School.